Okay, so we are going to pick back up for the second part of the lecture talking about specific electrolytes in the extracellular fluid. So as I mentioned before, electrolytes are just the name for ions in water. So the electrolytes form when the molecules dissociate, which means they break down into their ionic components. So a cation component, the positive component, and the anion component, the negative component. So examples you have are like your inorganic salts, something like sodium chloride, for example, breaks down into the positive sodium cation and the negative chloride anion. You'll also have lots of inorganic acids and bases, which we'll talk about in a second, and then some proteins can dissociate as well. Then you have your non-electrolytes, which, as the name suggests, they don't dissociate in water, meaning that they don't break into their ionic components. Examples they have are your lipids, so your fats, your urea, and then your carbohydrates like glucose. We're going to talk about two ions. Your book has more, but the ones we're going to focus on for this chapter are your sodium ions and your potassium ions. So with your sodium ions, they are the dominant extracellular cation. They have a lot of pressure on the osmotic pressure because they are so prominent. So when you have a lot of sodium needing to be excreted or needing to be absorbed, water is going to oftentimes carry itself with sodium due to that high osmotic pressure. So when sodium needs to be excreted, the kidneys are going to be the major source of getting them into the filtrate and into the urine. And when that happens, oftentimes when the kidneys excrete the sodium, water is going to follow suit. So water is going to join that sodium with being excreted. Same idea when it needs to be reabsorbed. So if you have aldosterone present in the kidneys, sodium is going to be reabsorbed back into the bloodstream, as is water, because water is always going to follow that sodium. And because water is linked to blood volume, which is then linked to blood pressure, sodium is actually going to be able to affect blood pressure through that chain of connections. And we have two conditions involved with high or low sodium levels. The first one is hypernatremia. That's when the blood plasma has too much sodium in it. And then we have hyponatremia. That's when the blood plasma has too little sodium in it. Then we have potassium. So potassium is maintained in a much more tight range than your sodium. And your potassium is largely responsible for the resting membrane potentials. This is the difference in charges between the inside of a cell membrane and the outside of the cell membrane at rest. So you probably remember talking a lot about membrane potentials when you learned about the nervous system and how based on the charge that can fire an action potential if you get to the threshold. Potassium is one of those key players with that. Like sodium, aldosterone is able to affect potassium being secreted or reabsorbed. So when aldosterone is present in the kidney, you actually will have a lot more potassium secreted into the urine. And then like sodium, you have two conditions. If you have too high or too low levels of potassium, if you have too high levels, it's called hyperkalemia, so hyper being high. And then if it's too low, you have hypokalemia, hypo being low. So to show one of the feedback loops with potassium, here we have your blood potassium levels in this normal homeostatic range. And you have two scenarios. First, when the blood potassium levels increase, they get too high. Ultimately, what's going to happen is your aldosterone is going to be secreted, go to the kidney, and then cause more potassium to be secreted into the filtrate, thus go into the urine and be removed from the body, which is going to lower that blood potassium levels, getting homeostasis back on track. Then if you have the blood potassium levels drop too low, what's going to happen is the aldosterone is going to be secreted at a much slower rate. It's going to kind of pump the brakes a little bit. Since there's less aldosterone in the kidney, that's going to mean less potassium is secreted, which means levels are going to start to rise again, getting back into our homeostasis. All right, so the last thing we're going to talk about for this chapter is acid-base balance. And to go over basic definitions, When something is referred to as an acid, that means it's going to release or donate hydrogen ions, which are H+, into a solution. So as you probably remember from basic chemistry, the negative logarithm of the concentration of hydrogen ions is the pH, or how basic or acidic a solution is. So it's all about the concentration of hydrogen ions. When something is a strong acid, that means it completely dissociates. It completely breaks down into those ionic components. So an example like hydrochloric acid has one hydrogen ion and one chlorine, and that will break into H+ and Cl- when it gets in a solution. When something is referred to as a weak acid, it will release some of its hydrogen ions in the solution, but not all of them. And usually a weak acid will have more than one hydrogen. So in this case, we have carbonic acid, which you saw a lot when we talked about bicarbonate and blood buffers in the respiratory unit. So carbonic acid could potentially donate one hydrogen ion, or it can donate both. So it has the ability to only release some of it into the solution, not necessarily all of it. Then you have bases, and bases, the idea is that they're going to remove hydrogen ions from solution. They're going to take them out of play and reabsorb them. Much like your acids, you have strong and weak versions. So your strong bases completely dissociate into the solution. So they'll break into a cation component like sodium here, and then an anion component, which is called hydroxide. So hydroxide is an OH group. And that hydroxide has a negative charge overall. Then you have weak bases, which, much like your weak acids, only partially dissociate. So they are able to reduce the concentration of your hydrogen ions, but they don't, again, totally dissociate. So to show you that in a more formulaic layout, here we have strong acids here, HCl, like your hydrochloric acid. When that gets into solution, it dissociates completely because it's a strong acid. So all of the hydrogen ions break apart from all of the anions, in what's referred to as complete dissociation. Then we have a strong base. Example here is sodium chloride, so NaOH, that breaks down into the sodium cation and then the hydroxide anion. Once again, complete dissociation. Then we have an example of a weak acid, like your carbonic acid, which has multiple hydrogen groups attached. And that can dissociate into one hydrogen ion and then bicarbonate. So we didn't totally dissociate because we still have one hydrogen ion attached to this CO3 group. And that you're familiar with it being bicarbonate. So this can potentially reabsorb another hydrogen ion and become carbonic acid again. Or it could then break down or dissociate more and donate this hydrogen ion again, and then have an extra H floating in the blood plasma or the solution. So there are three ways that acid-base balance is regulated, because we want to make sure that the blood does not get too basic or not get too acidic, because when it becomes too acidic or too basic, things won't function as well as they need to and can start breaking down and denaturing proteins. So we want to keep it within a certain tight range. The three ways this is done is through buffer systems, through the respiratory system, and then through your kidneys. So first is your buffer system. Your buffer system, by definition, is any substance that is able to resist a change in pH. What that means is that if we have extra hydrogen ions added to a solution, or the blood in this case, that buffer is going to take it out of play. It's going to reabsorb that hydrogen ion, so it's not in the solution anymore. If we have hydrogen ions being removed, the buffer can potentially replace them by donating another hydrogen ion to replace the one that's lost. So we're basically trying to resist any sort of change in pH by either adding stuff when it's removed or removing stuff when it's added. You have three types of buffer systems that your book talks about. First one you should be very familiar with, again, is your carbonic acid and bicarbonate, which is very important for maintaining your blood plasma levels. You then have proteins, which in some cases are able to absorb hydrogen ions. example your book gives is your hemoglobin, which is able to absorb a little bit of hydrogen ions, not a lot, but some. And then we have your phosphate group, which is another important buffer. Your phosphate group is able to pick up or donate 3 hydrogen ions, so 1 more than your carbonic acid. All right, so those are your buffers. Now we're going to talk about your respiratory system. So in part, this has a little to do with the carbonic acid and bicarbonate buffer system, and that's going to dictate how the respiratory system is responding. So when we have over here your blood vessel with your carbon dioxide and your water, we know that they can become carbonic acid and then dissociate into hydrogen ions and bicarbonate. When we have carbon dioxide levels get really high, higher than they need to be, we know that that pH is going to drop because we have a lot more hydrogen ions in the solution. When that happens, so things are getting a little too acidic, that's going to signal the brain, specifically the respiratory center. And what that is going to do is it's going to cause the lungs to increase their respiratory rate or do what's called hyperventilation. When you hyperventilate, you are now breathing in and breathing out at a much quicker rate, and you're getting rid of a lot more of that carbon dioxide out of the lungs. So since that carbon dioxide is leaving the system, you now have less carbon dioxide to form carbonic acid and then dissociate, making the blood more acidic. So that's one way that you can counteract the drop in pH levels. If you have a situation where the pH is getting too high, such that carbon dioxide levels are very low in the blood, maybe lower than they need to be, you can then have something similar happen where the brain gets signaled in the respiratory center. Then the lungs, in this case, are going to decrease their respiratory rate or hypoventilate. In that case, the lungs are going to slow down. We're not going to be breathing as quickly, and the carbon dioxide is going to remain in the lungs and thus the bloodstream, making sure more of this carbon dioxide can break down and dissociate. So last mechanism is by the kidneys. And much like with your lungs, you can have situations where the pH is getting too high or the pH is getting too low. So when the pH rises, meaning that it's getting too basic, your distal tubule of the nephron of the kidney is going to lower the amount of hydrogen ion secretion into the urine, meaning we're going to reabsorb more of those hydrogen ions and keep them in the blood. At the same time, we're going to decrease that bicarbonate reabsorption because bicarbonate is a buffer, and a buffer can uptake more hydrogen ions. So the combination of having more hydrogen ions be reabsorbed into the blood and less bicarbonate that could counteract that is being excreted, meaning that we're going to then lower the pH to counteract that basic level of blood. On the other hand, if our pH falls and becomes too acidic, the opposite's going to happen. So that distal tubule in the nephron is going to have a lot more hydrogen ions be secreted into the urine, so they'll get removed. And then we're going to increase the bicarbonate amount because bicarbonate can pick up more hydrogen ions in the blood. So the combination of removing more hydrogen ions out of the body and then increasing the amount of buffer we have to pick up stray hydrogen ions in the blood is going to ultimately raise the pH because we're taking more hydrogen ions out of the blood. So to ultimately recap all of that, because that was 3 different mechanisms, we have another homeostasis feedback loop. So here's your blood pH range. And if we have an instance where homeostasis is disturbed by having the blood pH get too high, so it's very basic now, we don't have a lot of hydrogen ions in the blood, the 3 mechanisms that can happen are first in the nephron of the kidney. So in this case, you're going to have a decrease in the hydrogen ion secretion and then a decrease in the bicarbonate reabsorption. The lungs are going to decrease their respiratory rate, and then the buffers are going to release more hydrogen ions. All that in combination is going to lower the pH because we're having an increase in the number of hydrogen ions in the blood. So bring it back down to the normal range. Then if our blood pH levels get a little too low, getting a little too acidic, blood pH is going to decrease. Hydrogen ions are now much higher in the blood. Three things will happen just in the opposite direction. So for your kidney, the kidneys are going to secrete more hydrogen ions, and then you're going to reabsorb more bicarbonate. The lungs are going to increase their respiratory rate, and then your buffers are going to bind more hydrogen ions. All of this together is going to increase the blood pH because we're lowering the amount of hydrogen ions in the blood, thus getting us back to homeostasis again. So very last thing for this chapter, briefly talk about acidosis and alkalosis. So acidosis is just the condition where any of the body fluids, like the blood, get below the 7.35 number. So 7 is roughly neutral when we talk about pH. The blood is usually able to go between 7.35 and 7.45, so it's slightly above neutral. But when we get below the 7.35 value, we are referred to the condition as acidosis. And this can be caused by respiratory or metabolic causes. Respiratory causes is just when we don't have adequate ventilation. So we're not removing enough carbon dioxide quickly enough. So so the carbon dioxide is becoming carbonic acid, then dissociating and getting a lot more hydrogen ions in the blood. So causes of this can be things like asthma, possible damage to the respiratory center of the brain, emphysema. There's a number of causes. Then you have what's called a metabolic acidosis. So this is just anything else outside the respiratory system that causes a decrease in pH. And there can be a mix of symptomatic versus conditional versus actual medical conditions that cause metabolic acidosis. So things like diarrhea and vomiting can be a reaction to metabolic acidosis. Ingesting too much of certain medicines, diabetes mellitus, example of a long-term metabolic acidosis condition, or simply something like anaerobic respiration, so just from exercise could cause acidosis. Then you have alkalosis, which is the sister version. This is when the pH of the body fluids is now above 7.45, so we're out of that sort of neutral, healthy range the body likes to be in. And again, it can be either respiratory or a metabolic. So respiratory can be caused by hyperventilating, so breathing at too quick a respiratory rate, or something even like being at a high altitude. Metabolically, you can have a bunch of different causes. So things like having too much aldosterone of the hormone and mechanism, or having something like ingesting substances like bicarbonate or soda that contribute to more basic levels. So takeaway message is that acidosis and alkalosis can be caused both by long-term and short-term conditions. And with that, that will end chapter 27. So I will see you all next time for the final chapter on sexual reproduction.